Hello friend, welcome back to your favorite technical channel AVM Tech Android. Today I am available with a video lecture for heat transfer by means of conduction, and in the 8th lecture we are going to discuss about conduction heat transfer. This is a QR code of my channel. Using this QR code also you can enter into this channel and you can see all the videos, or on the YouTube you can write AVM Tech Android and you can enter into the channel and you can take the benefit of all the free videos. You can share these videos to your friends or your colleagues, that will be helpful to students. So friend, in today's video we are going to discuss about heat dissipation from infinite long fin. We are discussing about extended surfaces or fins. In the last video we had derived the most general equation for rectangular fin with one condition. Now for second boundary condition we have to consider different case. In the different case we are going to consider the first case, that is infinite long fin. So friend, all these things which you can see, some formulas, some figures, all these things are related to this video, that is heat dissipation from infinite long fin, that is when L tends to infinite. So now let's start with the video. But before we will discuss about the video, the book which I am using is Heat Transfer by Dr. A.V. Mehta and Professor P.G. Choksi from one of the most reputed publication house, that is Books India Publication. You can purchase the book from Books India Publication Ahmedabad. And now we will start discussion. So friend, in the last video the link is available in the description box. You can find that the first boundary condition is available with us, and for second boundary condition we are having these four different cases. So out of all the four different cases we are considering the first case in this lecture. In the coming lectures we will go for second case, third case and fourth case. So at present we are talking only about case number 1, that is fin is very long, the temperature at the tip approaches that of the surrounding fluid. So with this case we will try to derive what is the most general equation for heat transfer in case of rectangular fin. So now let us consider the case, that is heat dissipation from infinite long fin, that is L tends to infinite. So friend, you can say this is a base. Over the base this infinite long fin is attached. So where what we learn, T0 that is a base temperature, TA that is air temperature or surrounding fluid temperature. This length tends to, this x tends to infinite. The second figure which you will see is the figure of temperature variation. You can see at the base temperature is highest. When the length is gone increasing, what you will observe is the temperature is dropping, and what you can see is when the length tends to infinite, when we are at infinite distance, the temperature is T infinite, and that temperature T infinite, that is almost equals to TA. So you can see the graph, that is a temperature variation along the length of fin. So friend, I hope this is very much clear to you. We are starting from here, that is x equals to 0 to x equals to infinite. So the boundary Conditions were known to us. First boundary condition was very much clear to us. When x equals to 0, the temperature is equals to base temperature. Now we are doing all this exercise for second boundary condition. So now here second boundary condition is when x equals to infinite, temperature is equals to ambient temperature, or temperature is equals to air temperature, or temperature is equals to surrounding fluid temperature. So now the most general equation that is available with us is this: theta, that is the temperature axis, T minus Ta, that is equals to C1 e raised to mx plus C2 e raised to minus mx. For derivation of this equation, you can refer the previous video. The link is available in the description box. And when we will put first boundary condition here, when x equals to 0, t equals to t0, we will get this equation, that is t0 minus ta, that is equals to c1 plus c2. Now what we have to do is, okay, we have to put this second boundary condition here. So in the most general equation, that is this theta, that is equals to c1 into e raised to mx plus c2 into e raised to minus mx. We have to put t equals to ta. So we will get ta minus ta, that is equals to c1 e raised to m into infinite plus c2 into e raised to minus m into infinite. Now we know this ta minus ta, that is 0. So you can see this ta minus ta, that is 0, and hence we will get c1 e raised to m into infinite plus 0, because m into minus infinite, that is 0. So based on that we will get c1 is equals to 0, and when we will put that value in the equation, we will get c2, that is t0 minus ta. So now two equations are available with us, and in that c1 and c2 values are available with us. So we have to put the value of c1 and c2 in the most general equation. So we will get theta, that is equals to, initially what was our equation, theta, that is equals to c1 e raised to mx plus, this is x, c2 e raised to minus mx. Okay, c1 is 0, this c1 is 0, so this term is 0, and c2 is t0 minus ta, that is theta 0. So I can write theta, this theta, that is equals to theta 0 here, theta 0 into e raised to minus mx, or you can write t minus ta, that is equals to t0 minus ta into e raised to minus mx. So in the dimensionless form, we can write this. This is a very important, which we have to remember. T minus ta divided by t0 minus ta, that is equals to e raised to minus mx, where T is the temperature at any distance x on the fin surface, Ta, that is ambient air temperature, surrounding temperature, T0, that is the base temperature, m, that is the fin constant, that is under root of pH divided by cross section area into K, unit is meter inverse. Okay, and x, that is any distance on the fin, that is in meter. So the first part is available, what is the temperature distribution. Our objective is to find out temperature distribution and Q, what is the heat transfer. So first target is achieved. So now we have to go for second target. So the heat dissipation can be determined in two ways, 1 and 2. So what is the first way? That is by considering the heat which is transmitted by convection from the surface of fin to the surrounding, means all the heat which is conducted, that will be convected. And second, by considering the heat flow across the base by conduction. So by base, from the base by conduction, the heat is dissipated. So we'll go with the second method, conduction. It is easy to us, we know it, because this is the Fourier's law. So Q fin at base, that is equals to minus Ka dt by dx at x equals to 0. So we know what is dt by dx. We know the equation T minus Ta. We had derived T minus Ta divided by T0 minus Ta. That is equals to e raised to minus m into x. So we have to differentiate this with reference to x, and we have to put equals to 0. X equals to 0. We have to put x equals to 0. X equals to 0. So what we will get is this. dt by dx at x equals to 0, that is equals to minus m into T0 minus Ta. T0 is the base temperature, Ta is the surrounding air temperature or surrounding fluid temperature, and m, that is a fin coefficient, or you can say fin constant. So put the value of dt by dx here. So we will get Q, that is equals to minus Ka into m into T0 minus Ta. So this minus minus positive. So Q, that is equals to K into cross section area into fin constant into base temperature minus surrounding temperature. And we know the fin constant m, that is under root of pH divided by AK, where P is the perimeter of fin, H is the convection heat transfer coefficient of surrounding fluid, K is the thermal conductivity of fin material, and ACS, that is the cross section area of fin material. So now we put the value of m, that is this value, and simplify it. So we will get most important second task, Q fin, that is equals to under root of PHAK into T0 minus Ta. So this equation represent heat transfer through infinite long fin. This is infinite long fin. So here one very important thing is mentioned. So let us read it. An infinite long fin is one for which m into L tends to infinite. How we will consider this fin is infinite? That is m into L, that tends to infinite, and this condition may be approached when m into L is greater than 5. That is fin coefficient and length of fin, when we multiply both of them, the value is more than 5, means we can say that this is the first case where fin is of infinite long length. So now I hope it is very much clear to you how to find out Q and how to find out the temperature variation for the first case when the fin is infinite long one. So now friends, I hope the first case is clear to us. Now based on that, let us try to solve some numerical, and very important thing, how in the exam we can identify whether the fin is of infinite long length. So you must see the video till end. So at the end I will tell what is the logic, or what is we have to keep in mind in fundamental. So as soon as we'll read the data, we can identify the case, because for fin 4 different cases are there, and we have to identify out of all the 4 cases for which case we have to solve the problem for, because for all the 4 different cases, there are different equations, there are different formulas. So let us solve this problem. You can find 2 long rods, one made up of brass with thermal conductivity K is equals to 8.5 watt per meter Kelvin, and another is made up of copper with the thermal conductivity 375 watt per meter Kelvin. So you can see here brass and copper thermal conductivity values are much differ, have one of their end inserted into the boiler. So the question is very much clear to us. For both the long rod, one end is fixed into the boiler. both of these rods are exposed to the same environment, means outside to the road either air is there, water is there, or whatsoever is there, but that environment remains same. Now at the distance 10.5 centimeter away from boiler end, the temperature of the brass rod is 120. So it is clearly given that from the boiler end, when we will go for 10.5 centimeter away, for the brass rod temperature is 120. So now the question is at what distance from the furnace end the same temperature could be reached in the copper rod. Assume both rods have same diameter. Means here the case is like that. You can say the boiler house is there. This is your rod 1 and this is your second rod. Okay, one is of, you can say this is of, you can say copper, one is of brass. So everything remains same, only the difference is material. So for this brass rod at 10.5 centimeter distance from the boiler end, here the temperature is 120 degree Celsius. Now the question which is asked to us is at what length same temperature is there. So friend, we have to find out just what is the distance where the temperature is 120. So now friend, guess and tell me, okay, the distance which you will get is less than 10.5 centimeter or more than 10.5 centimeter. It is not needed at all to solve the problem. You can say this kind of question will be asked to you in your personal interview or in your viva at college or in school. Okay, there is no need to calculate. Just tell me distance will be more than 10.5 centimeter or less than 10.5 centimeter. So you write your answer in one paper and then we will solve it, and then you check, you verify what you had guessed based on your fundamentals related to heat transfer and thermal conductivity, because only these two fundamentals you have to use, thermal conductivity and knowledge of heat transfer. So on one page you write distance is more than 10.5 centimeter or less than 10.5 centimeter. And when we'll solve it, we will get some answer. Then you verify the distance is less than 10.5 or more than 10.5. If your answer is correct, means your logic is correct, your fundamentals are clear, then you face no problem in the future also. So let's solve it. So friend, here the sketch is there. What we have discussed, same thing is there. This is a brass rod, this is a copper rod. At 105 millimeter, 120 mm degree Celsius temperature is observed. Same diameter is there in both the case. Outer condition is also same, only thermal conductivity is different. And what you have to find out is what is the distance at which same temperature will be observed. So let's see. Here I think not 37.5, it is 375. So K1 is 8.5, K2 is 375 watt per meter Kelvin. Now here the fin length is not given. So, and we'll learn only a first case. So we consider it is a case of infinite long fin. The most basic equation is known to us, d square theta by dx square minus m square theta equals to 0. Solution of this equation, second order differential equation, is theta, that is equals to c1 e raised to mx plus c2 e raised to minus mx. Boundary conditions are known to us. When x equals to 0, theta equals to theta 0. When x equals to infinite, theta is 0. From that we will get this equation theta, that is equals to theta 0 into e raised to minus mx. This theory we already learned, but there may be a case in the exam that you derive the formula and then you solve it. Then you have to derive the formula and you have to solve it. So you can see this is the formula which is derived. T, that is equals to Ta plus T0 minus Ta, that is equals to e raised to minus mx. If you simplify it, further simplification will give you answer T minus Ta divided by T0 minus Ta equals to e raised to minus mx, what we had derived. So now in this equation what we have to do is, we have to put T and x value, that is T is 120, that is equals to Ta plus T0 minus Ta e raised to minus m1 into distance in meter, that is 0.105 meter. Now if we go for equation number 2, what we can see is this is T, this is T, temperature. Okay, this is a temperature T 120, but what is the distance, that is not known to us, so I am writing L meter. So now this is your one equation, this is your second equation. We have to compare these two equations. So you can see when we compare these two equations, 120 common, Ta cancelled. So only remaining thing is this T0 minus Ta into this term, T0 minus Ta into this term. So again T0 minus Ta is cancelled from both the side. So we are having only this part. This is E. Correct? So e raised to minus m1 into 0.105, that is equals to e raised to minus m2 into L. Again E, we take ln, that is log base E on both the side. So E will be cancelled. So minus minus is also cancelled. Minus minus is cancelled. So 0.105 into m1, that is m2 into L. So L, that is equals to m1 upon m2 into 0.105. So what is m? That is a Fick constant, and that value is this under root of pH divided by AK. M2 is also again under root pH divided by K2 into cross section area. So if we go for m1 by m2, you can see P and H, that is a perimeter and convection heat transfer coefficient is same in both the case. Cross section area of both the fin remains same. So only available is K2 and K1, that is under root of K2 and K1, that is 375 divided by 8.5, that is 2.1. So this L, that is 2.1 into 0.105, that is 220 mm. So what we had discussed, you can say this is your brass rod, this is a copper rod. For brass rod, it 10.5 centimeter temperature is achieved, but for copper definitely this distance is long, because thermal conductivity of copper is high, and because thermal conductivity is high, it is offering less resistance to the heat transfer, so easily heat can travel a long distance, and because of that for this copper rod at large distance compared to the brass, we can achieve the same temperature. So here temperature 120 will be observed at 220 mm, almost you can say double. If I will tell this is 110, then this is 220, means compared to the brass almost at double distance same temperature is achieved. So if just you know this part, for copper thermal conductivity is high, so the resistance offered to the heat transfer is less. Because of that, as the resistance offered is less, the same temperature is observed at large distance. And if this is your logic, if this is your fundamental, then definitely you can rock the field. Let us go with the second numerical. It is very easy, again like previous case. It is a practical case which we can consider with our routine life also. It is required to heat the oil above 300 degrees Celsius for frying purpose. Means we want to fry something, and to fry we require temperature 300 degrees Celsius. So a ladle means a vessel in which we have to go for frying. It is like a vessel which we are using at our home, but that is with handle. Okay, so a ladle in which we have to put the oil, and oil temperature we have to reach up to 300 degrees Celsius for frying purpose. Now this ladle has a handle, and handle cross section is given 5 mm into 18 mm. Now surrounding is 30 degrees Celsius. Conductivity of the handle is 205 watt per meter degree Celsius. If the temperature at the distance 380 mm from the oil should not reach 40 degrees Celsius, determine the convection heat transfer coefficient, that is H. We have to find out H. But what is important thing which is mentioned here, you can say on one side you can say the vessel is there. Here the vessel is, you can say, with some handle. You can say this is a vessel with some handle. So here our hand is there. We had pick up the vessel. Here inside the vessel oil is there. So at this distance, you can say this distance is 380 mm as per data, where temperature must not go beyond 40 degrees Celsius. If the temperature is more than 40 degrees Celsius, what happens? We cannot handle the ladle. If we not handle the ladle, it is difficult to go for frying. So what we have to do is we have to find out what is the H value in this case. So friend, I hope this logic is clear to you, data is clear to you. This is your ladle in which oil is filled, and we have to go for frying of something, where this is a handle, cross section is given. We have to find out H for the case where the temperature here should not go beyond 40 degrees Celsius, that is given in the data. So it is a very simple case. Let us see what is given to us in the data and what we have to find out. As here ladle is there, you can say here ladle is there. Okay, here ladle is there. So here we have to put oil. Okay, so this is a ladle. So this is the base temperature 300 degrees Celsius. This is the handle of the ladle. This is handle of the ladle. Okay, here we have to maintain 40. Here we have to maintain 40. So this length is given, cross section is given. X is 0.32 meter. Temperature we have to maintain is 40. We have to maintain this temperature 40. Surrounding temperature is 30. Thermal conductivity is given 2.5. So what is H value that we have to find out? Simply we have to go for this formula, T minus TA divided by T0 minus TA, that is equals to e raised to minus mx, where to make this minus sign to plus sign, we will reverse this equation. So T0 minus TA, the numerator will come in denominator and the denominator will come in numerator. So this is positive now. So this is 300 base temperature, surrounding is 30, we want to maintain 40, surrounding is 30, X value is 0.320, M equals to Ketla. What is the value of M? That is fin constant. So we'll get M fin constant value, that is 8.673 meter inverse. Now what is M? That is under root of PH divided by AK. So remove under sign, this under root remove. So here this is a square of this, that is 7 75.22, that is equals to pH divided by AK. H is not known to us. P is the perimeter, that is 2 into B plus Y, you can say. So 2 into 18 plus 5. Cross section area, that is B into Y. K is the thermal conductivity, 205, and that is equals to 75.22. That is this value. So we will get the required answer H, that is equals to 30.17 watt per meter square degree Celsius. This is our required answer. So I hope, friend, this is very much clear to you how you have to solve this kind of problem. This is a very simple problem. Only important thing is you must know how to calculate perimeter, how to calculate area, what is the different temperature values. Once it is known to us, easily we can solve it. Now one more numerical we will discuss. Friend, I hope you are enjoying this and you will get the knowledge also how we will solve the problem. So a circular shaft means the perimeter and area which you have to find out, cross section area, for which you have to use the different formula, because previous case was a rectangular fin, now it is a circular shaft. Thermal conductivity is given, diameter is given, having 60° rise in the temperature due to friction. The heat transfer coefficient is 6.5 watt per meter square Kelvin. Determine the expression for temperature distribution and the amount of heat dissipated through the shaft, means Q we have to find out. Assume the shaft rod is of infinite long length. Here clearly it is mentioned it is infinite long length shaft, so there is no need to worry which case we have to consider. It is an infinite long case. Now this is a case in which you will observe the circular shaft with the diameter, thermal conductivity, rise in the temperature, convection heat transfer coefficient, everything is given. Just you have to find out Q. Very simple numerical, friends. Just the derivation of the formula. This is a derivation part which is known to us. The first boundary condition is x equals to 0, theta equals to theta 0, x equals to infinite, theta equals to 0. We know what is the value of C1, what is the value of C2. We had derived this formula, theta that is equals to theta 0 into e raised to minus mx. And for the Q that is equals to minus ka d theta by dx at x equals to 0. And based on that we will get the value of Q that is equals to Ka into m into theta 0, where m is under root of pH divided by AK, where P is the convection heat transfer coefficient, A is the cross section area, P is the perimeter, K is thermal conductivity. So this is convection heat transfer coefficient, this is thermal conductivity, perimeter is pi into, actually it is not pi theta, it is pi d. Okay, this is a pi d and area is pi by 4 d square. So pi cancel, 1 d is cancelled, so we will get 4h divided by kd. H value is known to us, diameter is known to us, thermal conductivity is known to us, so m value is available with us. Now you put all the values here. So K value is 50, A is pi by 4 d square, m value is 2.8, so it is 2.844, and theta 0, that is T0 minus TA, temperature rise, T0 minus TA, that is 60° Celsius, that is given. So directly we will get the answer Q value. What is heat dissipation from the circular fin, that is 24.97 watt. So friend, you try to calculate this kind of numerical at your home, at your room, at your institute by your own, and you try to find out whether you will get the same answer or not. So friend, I hope you are enjoying this lecture, and this video is very much helpful to you for your future growth. So now before we'll end this session, I would like to know how to find out the case which is of infinite long length fin. Friend, if you refer all the three numerical, you will in no case the total length of fin is given. This is a very important thing. If you refer all the three numerical, you will observe that in all the three numerical, in no case what is the total length of fin that is given. It means that we have to consider the case of infinite long fin. So friend, in exam when you refer the data and if you find that what is the total length of fin that is not given, if this is the case, means immediately you must understand this is the first case, that is fin is of infinite long length, and we have to use the formulas T minus Ta, that is upon T0 minus Ta, that is equals to e raised to minus mx, and this q value that is equals to under root of phak T0 minus Ta. So the important fundamental thing is discussed to you. Now if you like this video, then do not forget to subscribe this channel, share the channel and like this video. Plus you can use this, again I am telling, you can use this QR code of my channel to directly enter into this channel, or on the youtube.com you can write AVM Tech Android, you will see the site, you can subscribe it, you can see all the free video lectures available for this and for other subjects. Thank you very much, have a nice day.